So let's talk about mathematical models and how differential equations can help us model phenomena mathematically. Mathematical models are mathematical descriptions of a system or phenomenon. I like to think of mathematical models as existing between the real world and toy models on a continuum of complexity. So toy models are basically mathematical descriptions of our universe that are unrealistic and intentionally so. For example, we can consider gravity in one time and spatial dimension. Now, that's unrealistic because we live in three spatial dimensions and one time dimension. Nevertheless, we could consider this toy model because it will help us solve Einstein's equations in this unrealistic universe to kind of get an understanding of the property of these equations. On the other hand, we have the real world. So say, for example, you want to model projectiles, the trajectory of objects falling under gravity. Now, in the real world, you'll have, say, a ball. It's composed of a bunch of atoms. Within these atoms, there are subatomic particles. Within the nuclei, for example, there are quarks. The world is complicated. If you throw that ball, you'll also get some air molecules hitting it and others not. Now, we don't want to get into that level of granularity if we only just want to predict the trajectory within a reasonable amount of accuracy. Okay? So we're not going to, for our model of throwing a ball, consider all of these complicated dynamics that would go into, subatomic particles and different molecules hitting it. So we make some simplifying assumptions and we arrive at our mathematical model. So in that particular example of an object being thrown under the force of gravity, we could say, right, that the force of gravity is equal to the mass times gravity and pointing down. And we also have Newton's second law, okay? And what we could do is plug the force into Newton's second law, and we'll end up with ma is equal to negative mg. The masses could cancel, and then we have ourselves the acceleration, which is the second derivative of position with respect to time. Okay? And now say we do want to consider molecules hitting the ball and slowing it down. We want to consider air resistance. Okay? Now, are we going to get down to the molecular level where we're explaining every single interaction? No, that would be too hard. What we could do is make another assumption that air resistance is proportional to the velocity, okay? So that's just an assumption that we could make. We set the constant of proportionality to this constant b, and of course the velocity is the rate of change of position with respect to time. And with that additional assumption, we could then modify our equation to have a term that looks like this. Okay? And you see how it works? Does this capture every single molecule? No. But it's a good mathematical model. Okay? All right? It's fairly realistic, and it works in a wide variety of applications. So as part of our mathematical models, there are three main components you want to think about with mathematical models. One, the variables and parameters. Variables are the things that are changing, the things that we are solving for. Parameters are things that we fix, okay? They're constants of our models. For example, if we consider gravity an object moving under gravity and air resistance, one parameter would be g, the acceleration due to gravity. Another parameter would be b, the coefficient that quantifies how the air resistance relates to the speed of an object moving in the air, m, the mass of an object that's moving in the air. And so that's the difference between variables and parameters. Parameters are generally seen as things that you fix in your model. Doesn't mean you can't see how your model will change as you vary parameters, but they're generally considered fixed. We also make assumptions and hypotheses. Okay, so for example, here we assume that the air resistance is proportional to the velocity. We could have also assumed that it's proportional to the velocity squared or velocity cubed or e to the v. Okay, but here we'll assume this relation and see how accurate our results are. If they're accurate for our purpose, good. If not, we may modify them to get more accurate results. And 3 are rules of evolution. Okay, that's basically the equations of motion. Right. So here we would have this differential equation that gives us the rules of evolution. So in deciding the variables of a mathematical model, it is important to recognize the level of detail or level of resolution. Okay. So again, going back to that example of a ball being thrown in the air, the level of resolution is how small we want to get, how granular we want to get. Are we going to include molecules in the ball? Are we going to include molecules in the air? And then, use a Boltzmann equation or something from thermodynamics to characterize how the particles in the air are moving. That's too granular. If we just want to know where this ball is going to land, that's taking it too far, and we'll end up adding a lot of computation for very little reward. It makes no sense. We just want accurate results, and we're going to go the route of as simple as possible, but no simpler than that, right? When we model. So here, we're just considering the ball in the air. We're not going down to the granular details. Now, someone might be interested in, for example, how a ball would compress under stress or strain, and they may consider molecular bonds. Okay, so they may get down to that level. But for our purposes, we don't need to get to that level of detail, and so we're going to choose a higher level of resolution. And among mathematical models are dynamical systems. Dynamical systems are time dependent. Okay, so the example here, we have the position with respect to time, depends on time, so it's time dependent. If we're looking at population dynamics and how things are changing with respect to time, that's also time dependent. Not every mathematical model has to depend on time. We could consider, for example, the stress and strain in a rope, and we'll look at a static picture there. So dynamical systems are distinguished from other mathematical models in that they depend on time. That's the crucial aspect of it. And you're generally given the state variables at an initial point, and you want to know how these state variables will evolve and what they will be in at a future point. So when we model, for example, let's take a look at population dynamics here. We generally use what's called the 5-step method. And the first step, okay, and I'll write it over here. The first step is to ask the question, okay? We have to start with a problem that we want to solve, okay? And so here we could ask, for example, what is the population going to be in the future? Okay, so we ask the question. As part of asking the question, we'll state what our variables are, state variables. We'll also state our parameters. That's also part of asking the question. And we'll make some assumptions, okay? For example, we could assume fixed percentage growth, that the rate of change of the population is proportional to the population that's currently there. This symbol means proportional to, okay? That's an assumption we make. Is that a good assumption? Well, only if there are abundant amount of resources, okay? This will lead to exponential growth. So, although we could assume and write our assumption in a very kind of succinct way, this by just saying that the population is proportional to the rate of change of the population is proportional to the population, we also have to think about what it means, okay, like physically, what's actually going on. And what we're basically saying there is that we're never going to hit a limit. Okay, there are abundant amount of resources, and it's a fairly good assumption for situations where the population is not very large, you're not reaching any environmental constraints, the population's healthy and just growing, okay? So we make assumptions as well. That's also part of the asking the question. Then we select our modeling approach. Okay, now what goes into that? Well, we're going to say we'd like to model the population using differential equations. Okay, so we'll fix the rate of change to the population by, instead of going from proportional, we'll go to equals by setting that constant of proportionality. Okay, giving us our parameter here for the rate of growth. Okay, and so that's selecting the approach. Are we going to use differential equations? Are we going to use some sort of algorithm? Are we going to have a continuous model or a discrete model? Okay, a discrete model, basically you have rules of evolution where you'll get say p of t plus 1, or to make that clearer, n plus 1 is some function of the previous step. Okay, so you have discrete points. You evolve the system in chunks. A continuous model, on the other hand, these durations of time in between iterations are infinitesimally small. So if we solve this differential equation, we'll get an exponential, and that will be a continuous model. Okay? Whereas if, for example, we just say Pn plus 1 is equal to Pn times 1 plus r, okay, that's a discrete model. A continuous model would be P of t is equal to P naught e to the rt, okay? That would be continuous. Okay, so that goes into our selecting the approach. Thirdly, we'd like to formulate the model. And as we formulate the model, we just basically write the differential equation there. Fourth, we solve the model. Okay, and here we would get the continuous. So here, if we choose the continuous approach, we would have that solution. And 5, answer the question. Okay, say we start with a population of 10, and then 10 years later, how much would the population would be? We'll have our rate of growth. We'll find what rate of growth we could plug in there. We might do so by collecting observations, or doing some analysis on the data, and we'll plug in our t and answer the question. So this is how modeling works. We might realize, that say we want to predict the population. We start with a small population. We would predict the population after a long time. We might realize that the populations actually slow down. The rate of growth actually slows down, okay? And that happens, for example, when you hit environmental constraints. And so we'll introduce another parameter, okay? Say K, which is the carrying capacity. And we'll introduce we'll formulate another model, okay? Here we would have the carrying capacity model, okay? Or logistic growth, sometimes it's called. In general, so here we have an extra parameter. Here we only have one parameter, here we have two. In general, the approach should not be how can I be as realistic as possible, okay? Again, that goes back to what the real world, if you want to throw a ball, it has a bunch of molecules. You never want to make additional assumptions if you don't have to. You never want to include additional parameters if you don't have to, okay? So if we run our exponential growth model and, clearly we haven't hit any environmental constraints, or due to technology, the environmental constraints are not manifest, well, then we'll just use this exponential model, okay? And we're getting good results. We make accurate predictions. That's the ultimate test, okay? Can we make accurate predictions? Okay? Not how realistic is our model in the sense, does it incorporate every single thing that happens, okay? The actual population growth is complicated, right? You have so many different events. This couple gives birth. This person dies because they got, into an accident, and that's too complicated. We look at the aggregate behavior, and we just sweep all of that complicated stuff into simple parameters, okay? Now, someone might want to get into that granularity if they're modeling a certain specific micro phenomena, okay? For us, we just want to predict the population. And so we may elect to go to a more complicated model with an additional parameter if we realize that the rate of growth is changing significantly. And so we could start with exponential growth or fixed percentage growth, and we could check how our model behaves after some characteristic time. Now, if you notice, R has units of 1 over time. You can check that because the left-hand side here has units of number over time, and population is just number. And so R has units of 1 over time. So 1 over R, we could set that equal to some characteristic time so that we could say, we found that this model is valid. It's probably valid for, certain multiple of characteristic times. After that, it becomes not valid, okay? So here, we could look at radioactive decay. And just something to note about radioactive decay is that the form of the equation looks exactly the same as the fixed percentage growth, okay? The only difference here is that we make an additional assumption that K is less than 0, okay? And so you get parent nuclei, they go down in number, okay? So that our K is less than 0. Even the fixed percentage growth can incorporate a negative R, a negative rate of growth, okay, if the population is declining. So that includes both births and deaths, right? You could separate the two, but if you have more births than deaths, R will be positive. If you have more deaths than births, R would be negative, okay? You simplify things that way. And so that's radioactive decay. We also have things like Newton's law of cooling and warming. And here we have some body, okay, with a temperature T, surrounded by a medium that's larger and has a fixed temperature Tm. So we'll assume Tm is constant. That's a parameter, and it's the temperature of the surrounding medium. Now again, that's a mathematical assumption to say that T sub m is constant. It's often a good idea to understand what you're also assuming physically when you say something like that. I mean, if two bodies are at different temperatures and you combine them, in general, one will cool and the other would heat. Here we're saying Tm is constant. Is that realistic? Well, not exactly, but is it accurate? Can we get accurate results? If the medium is very large, it's a large reservoir, so that it could absorb heat from T or give heat to the smaller body T, but its temperature barely changes, then it's a pretty good assumption, and we'll make good results. We'll make good predictions. So here, after stating our parameters and our assumptions, we'll formulate the model and we could solve it. We also have a simple model for disease spread. Now, if you have number of people if X is the number of people who contracted the disease, Y are the people who have not yet been exposed, then it's reasonable to say that the number of people, the rate of change of the people who contract the disease is going to be proportional to the number who still have not been exposed times the number of people who have contracted it. Okay, and you fix that proportionality constant K. Now, this differential equation has two dependent variables, X and Y. Okay? It'd be nice if we could reduce the two dependent variables to one, and we can if we make another assumption that the total number population is constant. Okay? We're going to say that that's fixed, no one's getting in and out, and that X plus Y is equal to N. So that's an assumption. Okay? That plus one is to add one sick person who came into a population of N not sick people. And this will allow us to solve for Y in terms of X, and we end up getting this differential equation right there. Now we have a differential equation for X. What about chemical reactions? We could also model chemical reactions using differential equations. If we let X be the state variable for the amount of chemical C, okay, and we assume that 1A and 1B combine to make 1C, we could formulate this simple differential equation to work with, to solve this problem. Okay, so when there are no amount of C molecules, the rate of change for C will be highest at K times alpha times X, because X would be 0 there. K times alpha times beta, because X would be 0. On the other hand, if C is equal to alpha, okay, the amount of C is, so X is equal to alpha, and alpha is the initial amount of A, beta is the initial amount of B. So if we have as much C as any of the initial amounts, then this stops, okay, because you ran out of fuel for that reaction. There is no longer either A or B. And so there goes another assumption, right? That this reaction will terminate if there isn't, if one of those runs out. You don't get some sort of other complicated reaction or some secondary reactions. What about mixtures of brine? These are common. Brine is a mixture of salt and water. And you want to know the amount of salt in a tank. Okay, you want to know the absolute value, not just the concentration. but how many pounds of salt is in a tank? Well, you have a brine coming in. That's going to have a flow rate coming in, okay? There's going to be an input rate. How fast is the brine going in? And what is the concentration of that brine going in? And so what we end up with, okay, so the actual amount of salt in the tank is going to be the input rate of salt minus the output rate of salt. That's intuitive. And so how do we fix those? Well, we'll have Rn is equal to the salt input concentration. Say it's going to be 2 pounds per gallon, okay? So the person who's pumping in this brine tells you, yeah, that's what the brine concentration of salt is. And you want to know how fast it's flowing in, the input rate of the brine. Say it's flowing in at 3 gallons per minute. Okay. All right. This also has the solution that's flowing out. Okay. So salt's coming in and salt's going out. And now the tank itself has a certain concentration, right? And so R out is going to be equal to the amount of salt in the tank in pounds all over the volume. Now, the volume in general could change, right? If the amount of brine flowing in is greater than the amount flowing out, then we're going to get an increasing volume. But we could make an assumption and say that this has, say, a volume of 10 gallons. That's constant. Okay? Now again, whenever you make an assumption, you have to think about what you're actually assuming. Okay? This is basically telling us then that the output rate has to be the same as the input rate. Okay? Otherwise, you can't make that assumption. You can't just say that the volume is going to be fixed and somehow you have more flowing out than flowing in, or vice versa. Okay? So if we put all of that together, we could get a differential equation. It's going to be, so these gallons would cancel, and you get Rn is going to be 2 times 3, so 6 pounds per minute of salt flows in, minus, here you're going to have 3 divided by 10, or 0.3, and the gallons again will cancel, and so you get 0.3 per minute. Okay, that's just the unit that's there, and A of t is in pounds. And there you have then a differential equation that you can solve for this simpler model, which of course we could make more complicated by changing the flow rates. Maybe we could have changing concentrations, but it's just to illustrate what this equation is saying. Let's look at modeling for draining a tank using Torricelli's law. Okay, now Torricelli's law is basically telling you that the rate of change of the volume of some tank, this tank has a cross-sectional area of AW, that's AW, and it has a small hole, okay, it's important for it to be small, a hole at the bottom draining the tank, okay, with a cross-sectional area of AH, and it has a height, the height of the fluid there is H, okay, and we want to know the rate of change of H, the height of the fluid, how fast does it change? So Torricelli's law tells us that the volume, the rate of change of the volume is equal to the cross-sectional area of the hole at the bottom times the square root 2gh, where h is the height of the fluid. Now, notice that the volume is equal to the cross-sectional area of the whole tank times h, and we could use that. We could plug that in for v and then solve for dh dt, and we get this final result there. Now, it's important to make assumptions. One assumption is that this works when the hole is small. It can't be a very large hole. Okay. We also assume that the flow is laminar and steady, so we don't get turbulent motion. The fluid is inviscid, so it's not a viscous fluid. Viscous is kind of a clumpy fluid with there's a lot of friction going on in it. It sticks with things, so we assume that it's inviscid, none of that clunkiness, and incompressible. Okay, so air is compressible. You could take like a balloon and squeeze it. Okay, air does compress, but here we're assuming that the fluid itself is incompressible. It's not easy. If you squeeze it, whatever you squeeze in comes out. Okay, so you can't be compressed. And we end up with that relation. It's also common to get mathematical models for LRC circuits, and these are series circuits that look like this. We have a source of potential voltage, and we have a resistor, and we have a capacitor, and we have an inductor. Okay, and Kirchhoff's law tells us that basically the sum of the potentials is zero, or we get this differential equation here. We could then solve for Q of this differential equation. Q is the charge on the capacitor, and if we want the current in this, then we could just take the derivative of Q. Okay. We also have Newton's laws, which we discussed above. You could have an assumption that the air resistance is negligible, or you could include air resistance with a term like kV. Okay, so here we have a resistive force that's proportional to the velocity. Something to point out here is we could frame this problem as a first order differential equation with the dependent variable of velocity, or a second order differential equation with the dependent variable being position. So that just depends on what you're looking for, okay? Nevertheless, if you do, for example, solve for the position, you could always get the velocity as the derivative of position, okay? We could also model the slope of suspended cables, okay? Now, everything that we've looked at before have been dynamical systems, okay? Everything here depended on time, and it was a change in time. Well, here's a model that's not a dynamical system. And so suppose you have a suspended cable like this, and we consider 2 points of the suspended cable, okay? Point here at the very bottom and a point up here. And we want to know the slope at this point here, okay? We want to know the slope at this point here. Well, we have an angle, theta, okay? We can make this bigger. We have an angle theta, and we're going to say that that's dy and that's dx there, okay? And of course, we're actually considering these differentials. We just zoomed in there to make this point clear. And so that's where we get that tan theta is equal to dy dx, right? Opposite over adjacent. So we also make another assumption, and that's that this cable is suspended and it's not moving. So the net force is 0. We have this T2 theta, and so we have this is going to be T2 sine theta. This is going to be T2 cosine theta, okay? And T1 is tugging to the left, okay? And so the sum of the forces is 0 because it's not moving. So we have T1 must equal T2 cosine theta in magnitude. And we also have that along the y, the sum of the forces are 0. And so T2 sine theta is equal to the weight. And this gives us a simple model for, putting all of this together gives us a simple model for suspended cables, okay, that you see there.